Okay, we'll get started. It's an honor to have Tom Hope here from Hebrew University of Jerusalem. Tom is working with multi-turn intern from Microsoft Research and close colleague Daphne Shahaf. So we view him as a kind of a grandchild of sorts for scholarship. And he's been working on a topic that I used to brainstorm with Daphne about on analogy and creativity. It's great to see her following through this work, and you, of course, taking the leadership role on it, on boosting innovation and creativity with methods that come at the intersection of natural language processing, supervised learning, and crowdsourcing. And Tom is early in his career, yet he's already received a number of Best Paper awards, including KDD Best Research Paper and a number of Best Student Paper awards. And his work has already been appearing in multiple venues, including the Proceedings of the National Academy of Sciences, Wisdom, IJCAI, CSCW, and so on. He's beyond doing his PhD work, he's been leading an applied research team at Intel. Maybe we'll talk later about that and how you balance those two things. And before doing his PhD work, he did a master's in statistics. He's been involved in the Heidelberg Laureate Forum, and even had time to write a book for O'Reilly on TensorFlow. For all you folks that want to do TensorFlow for dummies, I guess. It's something like that, or a nice introduction to TensorFlow. Okay, well, Tom.
Okay. So, thank you again for inviting me. And today I'll speak about automating innovation and discovery with machine learning, which is the story of my PhD so far with Daphne Shahaf. Now, how many of you know this from Matt Might? Great. So, let's start by imagining a circle that contains all of human knowledge. And by the time you finish elementary school, you learn a little. In high school, you learn some more. And in your bachelor's degree, you then gain a specialization. And in your master's degree, you deepen the specialization. And then you read some research papers. You read, and you get to that boundary of humans' knowledge. That's where you start focusing. And you focus for a few years, and you push at this boundary, and you push, until finally, one day, this boundary gives way, and that dent you create is called a PhD. And that's me, hopefully, celebrating. Now, getting a PhD is great, but we have a couple of problems. First, as our knowledge keeps growing and growing and growing, it's getting exceedingly hard for any one individual person to reach that edge. And secondly, a lot of important inventions across history involve connecting the dots between two different fields and not just reaching the edge of one of them. For example, the ancient Greeks, more than 2,000 years ago, studied sound waves by analogy to water waves. And there are many examples, of course. The Wright brothers, for example, taking ideas from bicycles and transferring them to flight. We have NASA recently being inspired by origami to design parts of their spacecraft. And the problem here is that in order to connect between these fields, you first have to know of their existence in the first place, right? And then you have to have quite deep understanding in each of them in order to make proper connections. And this, again, is, of course, pretty hard to do and not really scalable for any one person across many ideas and many fields. Now, on the other hand, it's never been actually easier for us to get our hands on ideas. So we have millions of patents and scientific publications, crowdsourced innovation sites, and many, many more sources, all of which giving us an opportunity to accelerate problem solving, innovation, and discovery by giving people inspirations and identifying promising directions. But there's also a big challenge. These data sets are hard for people to work with. And the question is, can we help automate discovery and innovation on top of these idea repositories to help boost innovation? So in this talk, I'll speak about two directions we are taking. The first is boosting creativity with analogies. And the second is identifying novel ideas with the weak supervision framework that we developed. So let's start with analogies. A lot of important inventions across history involved analogies. We spoke about the Wright brothers and the ancient Greeks and NASA. Here are a few more important examples. For example, Thomas Edison said that an important quality of inventors is a logical mind that sees analogies, and he used analogies explicitly in his own innovation process. There's an analogy between slot machines to bacteria mutation that won a Nobel Prize. And closer perhaps to our own field, we have genetic algorithms and simulated annealing, all kinds of optimization approaches inspired by nature. And of course, there are many, many more examples. A different kind of example, a recent one, is of a car mechanic who came up with a device to extract babies stuck inside the birth canal to ease difficult childbirth. And the World Health Organization actually recently said that it's one of the most important inventions in this area in many, many years. But the really cool thing about this invention for us is that it came by an analogy. Analogy actually to some random party trick the mechanic saw online on YouTube, showing how to extract a cork stuck inside a bottle. And by analogy came up with a way to use this kind of mechanism to ease childbirth. So we'd like to take this kind of process of discovery by analogy and help automate it to these large idea repositories so that we can boost creativity. The problem with automation is that analogies are hard for machines. So NLP and information retrieval methods, as I'm sure we know in this room, do especially well at surface similarity, especially when we have similar source and target domains. For example, you could have this scraper that scrapes ice off your car, and then you could have burnt oil stuck onto a kitchen pan. And in both cases, we see this abstract case of removing a material stuck onto a surface, but described in completely different distributions of language. And we like to be able to find these connections. Now, what was done in the past, in the early days of computational analogy, was creating these kind of pretty crazy predicate logic kind of structures. For example, this is what the structure may look like for that cork extraction device. And as we can immediately see, this is pretty much infeasible. It wouldn't scale. It could take a huge amount of hours to extract for real products. So our first kind of quick attempt at this was, let's try some supervised learning to directly learn analogies. And we went to a crowdsourced innovation site called Quirky, which has many different categories, which is good because we want to learn analogies across domains. And they are written by ordinary people in the kind of messy variant of natural language, as you can example see in this text here. And we want to collect some labeled examples. So we built a search interface on top of Quirky, allowing crowd workers to get a seed product and then search for analogies. And when they find one, they give us a match. This way we collect our positive examples. We also collect negative examples, as in standard information retrieval, viewing the top results a user viewed but did not select as a match. And we also collect the query. So in this first work of ours, we learned a similarity metric reflecting analogy. I won't go into too many details about this one, but we trained a CNN-based network with the contrastive loss so that we can rank analogous products more closely than non-analogous ones. And importantly, we incorporated in the user query, because the user query is what the user inputted to search for analogies. And we use this as a kind of an anchor to help us focus on non-surface features, the more structurally related ones, at least according to the user, to cancel out the surface effects and find more abstract relations. So the good news about this work was that it beat standard retrieval baselines, and the query indeed helped us improve results. But the not so good news was that labels were costly and noisy and slow to obtain. It's a hard task for people. People tend to be good at finding superficial matches, like phones and different kinds of phones. Cognitive psychology studied this effect for many years. And because it's a slow and hard process, our data size is limited. And importantly, our model is left blind to the kind of rich structures that go into analogies. these abstract structures. And it's not really realistic to expect this model to learn it from raw text with the kind of data scarcity and noise that we have. So in our second work in KDD, we aim to go for a structural representation. So we want to find something that's expressive enough for analogy mining, but also simple enough to be learned. So somewhere in between that raw text and that very elaborate, crazy predicate logic kind of structure. And we end up focusing on the purpose and mechanism concepts. So these are deeply rooted in cognitive psychology that tells us that analogies are inherently related to the purposes and mechanisms of ideas. And in terms of purpose, we can simply think about what a product does. So for example, the scraper removes ice from your car, and the mechanism, how it works in this case, is with a brush, a blade, and a grip. Now, let's assume for a moment we have representations capturing purposes and mechanisms. We can do some core tasks like finding two products that share similar purposes but have different mechanisms, or do what's known in science and engineering as repurposing, finding two products that share similar mechanisms but have very different purposes. For example, that car mechanic coming up with a completely new way, new purpose for that extraction device. So our goal here is going to be to learn vector representations capturing the purpose and mechanism of inventions so that we can use them to find analogies and boost innovation. Now, we go back to Mechanical Turk and we collect data, this time collecting annotations of product texts with respect to purposes and mechanisms. And our goal here in this work is to learn soft vector representations capturing the overall aggregate kind of notion of the purpose and mechanism of an invention. And we do this simply by aggregating across our workers. So we learn TF-IDF weights for purposes and mechanisms across our corpus, having two sets of kind of importance, relevance weights for each concept. Then we take our pre-trained word vectors for each given product. We weight them according to purpose and mechanism across workers. And then we get two output target vectors, a purpose target vector and a mechanism target vector. And we want to train a regression multitask model to extract these two target vectors for new products. I'll quickly note, a technical note, that because we have a normalization layer somewhere here, normalizing our purpose and mechanism vectors, so by minimizing the MSE, we're actually minimizing the cosine distance. So we're finding things in the general overall direction of the purpose and mechanism, thereby hopefully finding some more abstraction. And we see that our approach is able to overall outperform standard retrieval by quite a large margin in most cases. And this is despite having noisy annotations. And importantly, because in our test set, people tend to focus on the more surface-based analogies. These surface analogies obviously favor the surface NLP approaches. And we are able to both recover the superficial matches, but also the more distant ones with our approach. Now, as a quick reality check, we also want to see what we were able to interpret here. So we take a kind of sparse coding approach, which you often see for understanding word vectors, and we model our target vectors as a kind of sparse linear combination of words in our vocabulary. And the bottom line is that we overall see that the mechanism words are indeed of a more mechanical nature than the purpose words. So our main evaluation and application goes back to our motivation of boosting creativity. And we do this in an ideation setting, which is a common creative task you often see in psychological studies and also in design firms. We give people a problem, for example, a cell phone charger case, which is a case that charges your phone. And we ask people to find new ways to solve the same problem. And we give people inspirations. So this is heavily based on ideation protocol and similar experiments. So we give people random inspirations. We give people surface-based, which is what you get from standard search, for example. And with our approach, we aim to find near purpose, far mechanism analogies, because we're looking to find new ways to solve the same problem. And our assumption or hope is that our approach will help explore the design space in a more diverse fashion. So sharing the diversity of the random approach, but also the relevance of standard search. So what kind of inspirations do we give people? Well, for example, random is of course all over the place. For example, one of the results we showed people was a dog meetup app, which I'm sure you all have installed on your phones as we speak. And we have standard search, surface-based, very relevant, more cases, more batteries and phones, not very diverse. And in our approach, we're able to first see that we get things related to charging, but not necessarily for phones. And indeed, one of the top results we were able to retrieve is a human pulley-powered generator suit. Now, this is kind of a silly invention, but it generates power using your movement. And the important thing here is that it doesn't mention phones at all. And in an abstract way is related to the problem of charging and creating power, just with a completely different mechanism, which is what we were aiming for. So when people, for example, viewed this inspiration, a bunch of them came up with ideas for generating power for your phone using your kinetic energy generated while you're walking. So to make this more concrete, we give all these hundreds of ideas generated by workers to a panel of external judges, and we have them rate according to standard ideation protocols, such as novelty and quality and feasibility. For example, you could come up with this time travel machine idea, and it could be great with respect to novelty and quality, but feasibility not so much. So we first observed substantial judge agreement with respect to these criteria across our judges. And looking at our results, both in relative and absolute terms, we're able to generate a considerable large positive effect, generating better ideas with our analogy-based inspirations. So the takeaway here is that our approach yields a substantial increase in people's creative ability using analogy-based inspirations. A quick note about another application we carried out is boosting scientific ideation. So here we want to find analogies between scientific papers, and we slightly refine our structure so that now we also include the background and finding annotations, which you often can of course see in scientific papers. And we work with a biomechanical engineering research group, helping them find inspirations and novel applications. Now this group had quite bad experience with standard search, like standard academic search, finding near direct replication of the lab's work. Whereas with our analogy-based approach, we were able to find results judged as both relevant and new. Out-of-domain alternative approaches that were never actually seen before by the lab and judged as potentially useful. So we saw models taking in the raw text, and then we added structure, the purpose and mechanism structure, and we slightly refined that for scientific papers. And now we want to take another step, and we're going to move from soft vectors to fine-grained functional models. So we're still going to Mechanical Turk, and we're collecting annotations of purposes and mechanisms, but we refine our structure in all kinds of ways discussed in our recent paper, which is under review. But now, importantly, our goal is to extract spans of text corresponding to purposes and mechanisms. So we want to find multiple fine-grained purposes and mechanisms. And this, importantly for us, enables all kinds of new applications, which we'll discuss in the next slides. Now, another step we want to take is to go to patent data, which is a really kind of important, large-scale source of engineering innovation. It's kind of an index of technology. And importantly, it's much larger than Quirky. So Quirky is challenging in terms of language and noise, but we want to be able to discover many, many more purposes and mechanisms so that we can find rich analogies. And the problem with patents is that, as I'm sure a lot of you know, it's a really messy kind of creature. So a common guideline for patent examiners and writers says that the subject matter of the invention should be described in one or more clear, concise sentences or paragraphs. Well, not quite the case. So here, for example, is one patent sentence. Forget about being concise. And about clarity, so patents often use this kind of obfuscated language, actually often done on purpose by lawyers who write these things. And take a look at this patent dating back to 2001. speaks about a circular transportation facilitation device. It goes on and on about this transportation facilitation device until you reach the pattern figures. And then you understand that what actually is going on is, well, reinventing the wheel. Yeah, this is a true story. It was an accepted patent. It later won the Ig Nobel Prize and only then was silently removed by the patent office. Yeah, so this probably goes to show you quite a lot about patents. So annotating purposes and mechanisms on Quirky was hard, so patents is going to be harder, really hard task for all the kinds of reasons I mentioned, and also patents often tend to kind of skirt around the purpose of the invention, often focusing on technicalities. So we try to ease this for ordinary people with sampling from domains that are easier for crowds to understand. Here's a few examples of them. Of course, this is on relative terms. We still get noisy annotations and often partial tagging. So workers often skip sentences, presumably because they're hard for them to read. So we realized that looking both at our quirky properties and our pattern properties, we could make use of the graph representation. This graph will do two things. It will capture the more local syntactic relations well known to exist for purposes and mechanisms, and we do this with a dependency parse tree representation. But we also want to capture semantic information, propagating semantic information across long spans of the text, which we hope will be particularly useful for patents with this kind of repetitious language across long texts. And we do this with an embedding-based similarity. And to make this more concrete, our graph is a contextualized graph convolutional network. So we take as input multi-channel input embeddings, such as pre-trained globe vectors, but also other pre-trained part-of-speech information, named entity recognition, dependency parse information. We feed all these embeddings into a BILSTM network to capture sequential context. And then the outputs emitted by our BILSTM are fed into that graph structure with a relational graph convolutional network. So we have multiple types of relations in our graph, and we want to propagate information across this graph. And we do this with multiple layers of GCN. And finally, each node in this graph corresponds to tokens in our original text, and these token representations are fed into a CRF to capture tag dependencies. Now, as a baseline, we first take a BILSTM CRF, we enrich it with all kinds of syntactic and semantic information, the same kind that we use. And in an ablation study, we also study the contribution of the different kinds of edges we use in our graph. And the bottom line in terms of accuracy is that our graph model was able to significantly improve results, and indeed for patents, using the long-range semantic edges, was able to boost our results further. Now, overall accuracy is quite low. We have our noisy training annotations and a noisy language. It's a really hard task. And our model predictions are often better than what we get from workers. So here's one example of a product annotated by us and by the workers. Let's zoom in quickly. So the crowd told us, for example, that the mechanism is a travel mug. But we are able to first extend this mechanism to a dual heated travel mug, and also add a purpose completely missed by the crowd, your coffee being warm on the go. So importantly, we're doing annotation in a noisy setting with untrained, non-expert workers on noisy, complex texts with noisy annotations. So this is pretty far from what you see in standard NLP. We're taking a scalable, low-cost approach here. And to evaluate, though, we want data which we can trust much more, so we go to a gold standard test set that we curate. And importantly, one final note is that we mentioned that workers have a hard time reading sentences and they skip quite a lot of them. So we add self-training, a semi-supervised approach to propagate our labeled information to training sentences that were not labeled erroneously. And we see this significantly improves results, especially for patents, where we were able to boost recall, which is what you'd expect. Now, we evaluated in terms of accuracy. Importantly for us, we want to evaluate in terms of usefulness of the model. And unlike those soft aggregate vectors which we saw before, now we have finer-grained vectors which support our applications, which is what I'll discuss next. So our first application is building a common sense functional ontology. So we're interested in mapping the landscape of ideas with an hierarchy of purposes and mechanisms. And these are often used in engineering, functional ontologies, but they are handcrafted. And these functional ontologies are useful first in terms of abstraction. So this can allow problem solvers to break out of fixation to one of those fields right at the edge there and connect the dots to more fields so that they can better innovate. And also reasoning. So understanding the interplay between purposes and mechanisms will potentially enable us to ask and answer complex questions on top of this graph. And here, for example, you can see a snapshot of a subgraph of what we were able to learn. So you have here this purpose node, which is here generating power and energy efficiency. Red corresponds to purpose, green to mechanism. We have a sub-purpose of generating power, which is charging your battery or devices in general. We have a sub-mechanism of generating power, which is solar power and mechanical stored energy and sustainable sources. Yet another sub-purpose of solar panels for solar power and storage batteries for stored energy, etc., etc. Now, to learn this ontology or any ontology, we first need a discrete representation of concepts. This we do by clustering our purposes and mechanisms. For example, that's how we got our solar power cluster. And we also need hierarchical relations. And this we do with rule mining. We observe the co-occurrences in our data between those purposes and mechanisms. For example, we can find out that mentions of protecting your head entail safety, but not necessarily the other way around. And we compare as a baseline to an approach based on part of speech tags, for example, telling us that verbs are typically more related to purposes and noun phrases typically more related to mechanisms. And we see first a large improvement over this baseline, but we also see good performance now closer in absolute terms. So you probably can't see those figures right there, but for example, for the purpose-purpose relations in our ontology, we're able to cross 80% accuracy. And importantly, we give this to judges who are research scientists and engineers, and we see substantial judge agreement with respect to the relations we're able to extract. Second application is building expressive search engines to help boost innovation. So say, for example, you are a light bulb manufacturer, and you want to expand to new markets. So you know all the obvious stuff. You know about lights for the office or flashlights. You want to find new places where light can be used, but light is not the main purpose. So it's pretty hard to do this with standard search. You need a more expressive language. So we enable to ask, for example, find me product ideas whose mechanism includes light, but purpose must not include light. And then, for example, you get warning signs on foods, warning about food content using light, or sanitization with light. So killing bacteria with UV light. These are two products we were able to retrieve. Technically, we work on top of a set of purposes and mechanisms and query terms, and we define distance metrics on top of them to solve retrieval problems. And to evaluate, we first construct 4 search scenarios common in ideation, these kind of templates, for example, using light for the purpose of cleaning. And we compare against standard search and also our own previous soft aggregate purpose and mechanism vectors, which we saw before, to see how much finer granularity is able to help us. And we have our distance metrics, which I won't go into right now. And importantly, we're able to see that our finer grained purposes and mechanisms are able to substantially boost results with respect to other approaches. So, to summarize this part of the talk, we spoke about raw texts fed into a machine learning model to find analogies. We then added structure, the purpose and mechanism structure. We then slightly refined it for scientific papers. And then we went on to finer grained representation. This importantly has applications in terms of ideation, boosting creativity, also in science, purpose and mechanism, common sense, functional ontologies, and building expressive search for inspiration queries. And importantly, this is work done with the help of my colleagues at the Hebrew University and also at Carnegie Mellon University. Okay, so we spoke about analogies. Let's take a deep breath. Now we're going to move on to the second part of the talk, which is identifying novel ideas with a weak supervision framework we developed. So let me start with our high-level motivation. We want to discover novel patterns, those patterns at the edge. And we're working on this right now. The problem with identifying novel patterns is that getting labels for pattern novelty is something really hard. So pattern novelty is kind of a hard concept to understand in the first place. And you could take a patent and all its prior art and show it to a domain expert, and it would still take a huge amount of time and effort to be able to rate this patent according to how novel it is. Now you could ask, why not just use citations? Well, citations are well known to be a very weak proxy for innovation. This is drastically true in patents, but also in science. And another problem with citations is, well, the community often doesn't realize the true innovative potential of an idea, or it could take a long time for it to do so, thereby greatly biasing and delaying this metric. But the good thing that we do like about weak proxies is that they are easy for us to obtain. So in this case, we focus on aggregate patent portfolio information. So we could go to economic research telling us that the average proportion of truly novel patents is really low. And we simply know, for example, that some academic institutes, for example, are more innovative than others. And we'd like to go from this rough aggregate information on groups to inferring on individual patents. For example, telling us that a patent about autonomous vehicles is, well, more innovative than reinventing the wheel. Obtaining labels, of course, is generally difficult. It's not only in this task. So you often have simply no access to ground truth information. So you could take user behavior on some app and ask an expert to rate this user according to who the user voted for or what are the user's underlying health conditions. That won't happen because that information is just not there and it's not accessible. You often have privacy issues with showing data to experts or the crowd. And in general, crowdsourcing is simply not a cure-all. So workers are not domain experts, and this process can be difficult and noisy and a costly process, as I'm sure we are all aware of. But getting rough aggregate information is often much easier for us to obtain. And we want to work with this rough aggregate information. And we developed for this a new framework we call ballpark learning. And the name ballpark comes from an educated guess or estimation falling within acceptable bounds. It comes from an analogy to baseball, and we love analogies, as we said, so that's the name we chose. And the general framework for ballpark learning is taking training instances X with unknown labels Y, and our instances are divided into bags, for example, patent portfolios, comprised of individual patents as instances. And we have constraints on the unknown label averages in these bags. For example, telling us about the average proportion of novelty, upper and lower bounded by certain constraints for a certain institution. We can also have difference bounds, bounding the differences of label averages and bags according to various encodings. And our goal here is to learn to predict instance-level labels from rough constraints on label averages given for groups. Okay, so let's start with our formulation in terms of classification. We have a discrete binary label space. This can also be extended to the multi-class setting. And we solve the following biconvex optimization problem. I'll just go into a few details here. Our objective term contains a hinge loss. Our objective function contains a hinge loss term and also slack variables. So we could have labeled examples in some cases, a few labeled examples. And we have proportion constraints, upper and lower bounds on proportion constraints in bags. And the intuition here is that the objective helps find an assignment to the latent label of vectors y such that it accurately matches model predictions. But we also have linear constraints to ensure correct assignment to that hidden vector of labels y to ensure that they fall within our ballpark feasible set. And we solve this biconvex problem with a coordinate descent alternating approach, which converges quite quickly in practice. Now, we also have a formulation for regression with continuous targets. Now, this problem is convex, in fact, quadratic with respect to the label y, which has all kinds of advantages. And we also have a formulation in terms of a feasibility problem. So now we're going to constrain our model predictions themselves to fall within our ballpark constraints. This has the advantage of having much less parameters. We don't need to estimate that hidden vector of labels. We also have a probably approximately correct formulation with a sample complexity bound that goes with that. And more details and discussions appear in our wisdom paper. Now, a final note is about hyperparameter optimization. So how do we find hyperparameters when we don't have any labels? So we develop a scheme we call constraint violation cross-validation. So what this means is we split our bags, our training bags, into training and held out subsets. And then because we sample these bags uniformly, we're going to assume the proportions remain approximately unchanged in the training and held out bags. And then we'll measure constraint violation on these held out bags, measuring how far off our model's predictions were in terms of the aggregate proportion predictions from the ballpark constraints. And then we simply pick the hyperparameter with a minimal average violation. Now, our end game is patterns, but first we want to evaluate in lots of benchmarks and data sets, so we have labeled examples. So we predict across lots of classification and regression tasks. Here is a small sample. For example, we predict recidivism, return to jail, according to groups of inmates, such as based on their prior record. We predict prices of apartments on Airbnb according to neighborhoods and other simple attributes. And we predict in a socioeconomic setting. And to get a bit of feeling for this, let me just get a bit deeper into one of these examples. So say you want to predict income as being either high or low in the well-known census data set. But now we're going to emulate the example. We don't have any labels at all. But we do have bags based on education and gender. So we can build these bags and constraints based on expert knowledge and prior knowledge, for example, coming from surveys or from previous census data or from sampling or even intuition, telling us, for example, that the proportion of high-income PhDs is higher than in the overall population. Or so my advisor Daphna tells me. I hope that's true. And we can build all kinds of other constraints. And importantly here, the bags we build are not necessarily used as features. Okay, so the model at test time can predict the label, in this case income, without knowing the education level of a new incoming individual or test instance. Okay, so it's kind of information used only during training. Now, to evaluate, we first see that we need quite a lot of labels in standard supervised learning, such as SVM, to match what we can get with no labels at all. And we also compare to a setting in machine learning called learning from label proportions, published, for example, in JMLR, where exact label proportions are assumed to be known. And this is a much stronger assumption than we take. We actually extend and generalize this work in all kinds of ways. And we see that we're able to rival all kinds of learning from label proportion approaches by making use of much less and much weaker information. Now, that was a case where we had expert constraints, but where else could we get constraints? Well, one case would be crowdsourcing. So we pool noisy crowd guesses on intuitive groups. So we ask people to predict return to jail, the likelihood of return to jail on average according to simple groups, or guess ranges, average ranges for prices of apartments according to simple attributes, such as apartments having a TV available on Airbnb. And the bottom line is that our results rival supervised models that use many true labels. And when we feed our individual labels collected from the crowd by showing them as in standard practice, here's an instance, here's an apartment, here are all its attributes, much more information than what we have, we actually get much poorer results. The crowd generated labels, when fed into our supervised models, generate really noisy results. And in addition, we do our weak supervision approach at a cost that is much less than that standard labeling approach because our questions are able to cover many groups at once with a kind of weak signal. So when would you use this approach? Well, when you have no labels, only rough information on groups, or when crowdsourcing for individual labels is difficult. So we need much less domain expertise because we rely on this human intuition on groups and comparisons, which is well studied in psychology. We ask much fewer questions, thereby cutting the costs. And we have virtually no privacy concerns because we really never show individual instances to workers. This can also help with all kinds of other difficulties and characteristics you'll see in these kind of tasks, such as continuous targets and crowd biases and outliers, which we discuss in our wisdom paper. And importantly, this approach can help complement standard crowdsourcing when these scenarios and difficulties come up. Okay, so towards the end of this part, our kind of end goal is using our ballpark approach for patents. And as I said, this is something we're working on right now. So where do we get our aggregate constraints? Well, first we go to economic research, telling us something about the proportion of novelty according to various scenarios and categorizations of patents. We also have all kinds of institution rankings, companies and academic institutions according to how innovative they are. That gives us constraints and bags. We also need features, so we connect back to our previous work on on analogies. So we can connect to work on recombination, telling us that innovation often involves connecting different mechanisms or using mechanisms for far untypical purposes which you wouldn't expect to see usually. Now, one final challenge, and of course we enrich our features with all kinds of other patent citation networks and textual representations, but a challenge here is that we have a small number of truly innovative patents, and we find that we need to gain a finer level of control on the distribution. So when we want to compare two companies, for example, we don't want to compare their averages. We want to compare only the top of their distribution because that's where the novelty is. And we'll do this with the sum of the top K ranked results, which is a convex function. But unfortunately, this puts us in a violation of convex programming. But luckily, we have dedicated specialized optimization approaches for this scenario. And as I said, work in progress, but our initial eyeballing of results is able to reveal higher recombination, all kinds of other novelty indicators for the patents we are able to retrieve, better than anomaly detection, for example. And we've started working with patent examiners to get better, more concrete evaluation. Okay, so in the next few minutes I have left, I'd like to quickly discuss some future work and also my own broader interest in taking this forward after completing this. So, in terms of analogies, we spoke about richer NLP models and representations. I'm interested in extracting graphs of purposes and mechanisms that describe the interplay of purposes and mechanisms in individual products and patents and scientific papers. Injecting external common sense knowledge graphs to understand these documents better and perhaps help us with better abstraction. We've started working on a live search engine for researchers and engineers and the general public to be able to find new ideas. And in ballpark learning, we spoke about a non-convex extension for patents, which we're working on. And we've also started working on learning deep neural networks from rough aggregate constraints on groups rather than collecting many individual instances as we would usually do. Now, in terms of my broader interest in taking this forward, so I'm interested in developing new models for complex texts and behavioral data in the domains of scientific knowledge discovery, health, social science, and psychology. Now, obviously, that's quite a lot. I'll just give a few examples. In terms of modeling complex texts, well, we spoke about scientific papers and patents. Obviously, there are plenty more examples like conversations evolving over time and medical documents and transcripts, many more examples. And graph neural networks, which is a promising direction in NLP right now, could allow us to propagate fine-grained information across long spans of the text and also potentially give us different levels of resolution about what the document is discussing. Now, one kind of area I'm interested in is, can we do a multimodal fusion of search behavior with scientific paper content? And an example question I'm interested in asking is, how do we search for new ideas? So sometimes I kind of call this researcher gradient descent. So you know when you have a new idea and you go to an academic search engine like the Microsoft academic search engine and you want to find if your idea is out there. Now we can take all these searches from researchers and see if we can model this process, this kind of search for ideas, looking for interesting gradients in the space of ideas. Can we find directions that we should look at in this complex space of ideas? Can we model this process of how we as researchers look for new ideas, discover these directions, predict how they evolve, and then use that to boost our own discovery process? And also in general search beyond the scientific domain. So people always have ideas. You have ideas for products, for startups, general ideas, and you would often go to standard search engines to look for ideas. So can we identify those sessions, those search sessions in which people are looking for new ideas, and then do that same kind of process of helping them discover new ideas and modeling how people search for new ideas? And graphs could be a useful representation here by matching search behavior with fine-grained information and content and propagate it in a learnable fashion. Now, another useful component where graphs could help us is by incorporating external world knowledge graphs and information into NLP models. For example, medical knowledge graphs or EHR, electronic health record data, fusing that into our NLP models to gain better understanding of the documents. Now, we spoke about boosting innovation and discovery, and one more way to do that would be by observing science in action. So taking a look at the trajectories of science, this dynamic, heterogeneous, continuously evolving graph of scientific knowledge, for example, the Microsoft academic graph. And asking, for example, can we predict the path of experts? So what will your next papers be about? Can I predict that? In some cases, it could be quite hard, but in some cases, maybe less so. And this has applications both for understanding science and how it evolves, but also potentially help boosting it. So think, for example, that you could emulate great researchers and how their methodology of searching in that space of ideas, this gradient descent in the space of ideas, and then helping boost our discovery process in general. Can we identify structural holes in this rich graph of scientific knowledge? These areas in space where it's interesting to look at, maybe connecting the dots between fields and not just any random connections. So you could come up with any crazy idea like, I don't know, a bicycle for elephants. So it turns out someone's thought of that one already. And secondly, who cares, right? We want the high value research potential areas. And finally, this is kind of even more ambitious. So can we learn generative models of ideas by observing this graph? Sometimes I call this the algebra of ideas. So learning how ideas compose together, or decomposing ideas into finer grained ideas. And can we amplify certain aspects of ideas? Imagine you have this knob which you can turn up a certain aspect of an idea. Where does that throw you in the space of ideas? And then can we sample in a controlled fashion from this generative model to point us into interesting directions in space? Finally, last part is we like analogies and we like abstractions. So let's take this to an abstraction of innovation and think about novel social phenomena and novel health-related phenomena and new concepts and new misconceptions. So, for example, can we take the anti-vaccination movement and understand it with NLP from online discussions, discover it and predict it and model it, maybe even discover analogies to other movements? Can we predict how people make decisions, and in particular, collective decisions? Can we predict collective behavior and collective decision-making from group conversations, identifying group dynamics and latent individual roles that are studied in psychology and group psychology? And a bit more generally, discover new health and psychological behaviors and symptoms and causes, where a useful component here would be to learn a broad knowledge graph of health-related activities and psychological states mentioned in context of what people do online and how they speak about things, discovering fine-grained pieces of information, how they all interrelate regarding health and psychological information. Finally, I'll quickly note, as Eric also said, that speaking about health and social knowledge discovery, I've also been leading an applied research team in industry, working on NLP, computer vision, and graph machine learning for healthcare and knowledge discovery from social media and the web. For example, we recently published a paper with a mixture of experts approach for an adaptive fusion of a lot of pre-trained vision models and NLP pre-trained language models to improve transfer learning across many different data sets. But I won't go into that one today. So, to conclude, we spoke about boosting innovation with analogies, extracting purposes and mechanisms from noisy real-world text, from products and patents and scientific publications, for enhancing creativity and expressive search engines and building functional ontologies. We spoke about weak supervision, a new weak supervision framework we developed, working with coarse label average constraints. We evaluated across many domains in regression and classification. And in work in progress, we developed a non-convex extension for patents to identify novel ideas. And in terms of broader interests, I'm interested in modeling complex texts and behavioral data for knowledge discovery in science and healthcare and discovering novel social phenomena. That's it. Thank you. Thanks. Any questions? Yep.
So I was kind of hooked on the last part there of your vision for finding relationships between different domains and predicting some useful connecting of dots.
Yeah.
I mean, you could look at let's find areas of common structure. Let's find that there's a functor from this area to that area, and we can find some mapping that these objects map to those, and these relations map to those, and maybe from this algebraic structure you find some proposed thing, when people have this kind of situation, they do this.
Exactly.
And they've done it over here, try it over there.
Yeah.
But how do you know that that's going to be valuable? And do you have any sense of how to predict some cases this relationship might hold and work well, but other times not?
So that's a great question. So as you'll see, I don't want to come up with bicycles for elephants. So you could think about a way to, maybe there's a problem of transporting elephants. So you could look at a previous work on transportation and use bicycles. Okay, so let's just put that together. But it's not going to have high value, right? So that's an interesting question of how do you model high value, usefulness, and impact, and how do you define it, and how do you predict it? So one way to go about that would be by, unlike our work on analogies in the sense that we just aim to discover general analogies, we also want to observe science happening in action. And if we can identify historically the scientific inventions and recombinations and analogies that had the higher impact, can we have a model that not only is able to retrieve those analogies, but also predict the impact and predict usefulness in a combined fashion? Now, that's not going to be easy, of course. It's good to start with crazy ambitions and then tone them down a bit when you're writing the paper. But in a sense, there is lots of historical information out there. The history of science and the history of technology and the history of inventions that actually ended up making impact in the world. Can we observe those and identify them and distinguish between them and those that didn't really make an impact? And then training our model to take that into account too. So that's a difficult challenge, but I think that's one direction to go about what you're saying. So, as you say, it's really a hard problem. How do you find the high value areas in space, not only the crazy creative ones? Yep.
I'm very excited about what you're doing, but for another reason, and that is that our planet's melting. We have 10 or 15 years before all of our children are facing a Mad Max future if we don't do something. And I think you actually are potentially contributing massively to that. The reason is that if we start with impact and work backwards and start filling holes that way, what is necessary to achieve that, or what is likely, or what is in the way, the kind of approach you're using can be very powerful. There's a coalition that Microsoft is a part of called BT Energy Coalition, which has tried to define roughly 5 major thematic areas and another 10 or 15 within each area of innovations, and that is actually product lines rather than cute inventions, product deliveries and practice changes that would massively reverse or substantially reverse some of the climate screw-ups we've made.
Yep.
What's interesting is what would happen if you started with some or many of those outcomes and started working back and seeing if you could start predicting white space, needed space, risk profiles using your approach. I think it would be enormously powerful.
Yeah, so first of all, I'd be happy if I can help improve the climate. And I do think that you're right, that analogies between ideas and learning what was done in the past to project to the future and discovering, perhaps, I had a conversation before about discovering materials, that maybe we can remove certain aspects of those materials that are more harmful in terms of their impact on climate, but keep their more useful properties. So we can think of this concept of discovering these abstract connections in a more general sense than just purposes and mechanisms, canceling out certain properties, but keeping the good ones, and then retrieving all kinds of inspirations of similar materials, for example, or similar approaches, and their own kind of profiles, as you say, that could suit our own approach. So I definitely think this has implications, indeed in general science, but also you would have to come up with adaptations for, as you usually do for any approach, for general domains and general verticals. And I think this one sounds like a promising direction. I'd be happy to speak more about it and see what kind of specifics could take place there.
Other comments or questions?
Could I ask a follow-up quickly? With regard to patents specifically, in our work, we run an organization called the lens.org, which is a unique amalgam of global patents and scholarship, and we do this in collaboration with commonsense team at Microsoft Academic. One of our observations is that the information content of patents is dramatically increased by removing boilerplate that is theme-specific. So we use classifications, which are a very powerful tool, to actually look at whether we can dramatically increase information content by removing lawyer bullshit. So each field of activity has a different syntactical norm. So in my field, I'm a biotechnologist, there's ways of framing biotech patents in terms of their embodiments and this and that, that is basically formalistic to get the grant of claims you need. Okay? By actually structurally thinking about removing those, you could possibly increase the information content of each textual sample dramatically, and not have to worry about as much of the noise. And have you started to toy with classification-specific bullshit removers?
Yeah, we have actually. That's a good one. There's a bullshit detection course taught at UW over there, so maybe I should start sending.
I'll just read a patent, you'll pick it up.
What's your task with the patents?
What is our task?
Yeah, I mean, why do you want to remove the boilerplate?
So human beings can read them that are not patent.
For kind of simplification.
Well, simplification is the wrong word. I think increasing the information content is the way. Because patents were originally conceived as a tool for business, not as a tool for patent professionals. And we'd like to restore it to its luster as a teaching tool.
So we actually did work with classification. So in terms of identifying novel patents, we definitely use categories. We also use them for our crowdsourcing to sample from more simple categories. But we also had not such good experience with categories, and we discovered that they often tend to be either super broad in many, many cases, or super fine-grained information, like basically repeating what the patent says in the kind of long CPC category, which seems kind of strange, as if there's only like a few. You take a patent family, small patent family, and they basically created a category just for that. And we found that being able to, at least for our goal of purposes and mechanisms, we gave these to the crowd instead of the text itself. We didn't get such good results because the super broad ones tended to focus too much on abstract concepts and not so much on the mechanistics, which we do want. And the super fine-grained ones didn't say anything about the purpose at all. And in between, we had a hard time finding the right combination. Sometimes it did exist, but for a lot, it didn't. But they definitely are useful for us in terms of learning features and also in traversing this kind of tree and graph and helping with abstraction. I do think there's more room for us to use these, especially for abstraction of categories. I will say that another thing we did to help crowds read patents is also by this kind of magical sentence and patents that often appears in the background, which tends to be much clearer. It's like the first sentence of the background. It often says, the purpose of this invention is, which, it's kind of obvious thing, but you have to look hard for it. Or this invention is built of something and something, and it's meant for this domain. Suddenly, magically in human-friendly language, and then suddenly it again vanishes back into legalese. So we take that sentence too, and we show it to the crowd in addition to the abstract and the title.
What's your sense on the prospect of cutting to the you might call the borders of understanding and novelty, and characterizing combinations of ideas, whether it be purpose or mechanism or other characterizations of patents in terms of what's actually the novelty itself,
Yep.
in terms of getting at what the contribution is, specifically in how it fills a hole that might have been a hole in obviousness.
Yeah.
We have this non-obviousness, right? It's non-obvious and X, Y, and Z. These characteristics
It has to be both novel and non-obvious, whatever that means.
So novel and non-obvious. So getting at the idea of that suggests there's something new here.
Yeah.
Which is not necessarily, which might be new with an old analogy, might be new in terms of mechanism, might be new in terms of even purpose.
Yeah.
And so the newness is interesting to me.
Yeah.
When I look at a new idea or learn something new, I have this idea. It seems that in some ways information theoretic in terms of a surprise function, where there's a pop of what, that's actually interesting and new. It gives me a new set of ideas that I can build on.
Yep.
I'm not sure what you've done that gets directly at that concept.
Yeah. So let me go back to this slide.
Yeah.
So let me quickly tell you about some of the directions we've taken, and this is indeed very important because we have thought about how do we tease apart what is the new part of the pattern. So first, I'll tell you about what we have been doing.
And I want it to be something that doesn't necessarily is not new legally or new in a court of patent law, but something that gets me excited. Like, I hadn't thought of that before. That's a whole new. Or other audiences that might see this contribution and light up and say this really is
for sure.
The novelty function lights up.
Yeah. So I'll say quickly what we've done, also some thoughts about how we could do this even better. So first we connect to recombination literature that again tells us that if you find two products that share similar mechanisms, that share distant mechanisms or use mechanisms for new purposes, that's a high indicator of novelty. So we're able, in a sense, with our information extraction approach, to slightly break down the patent into a subset of mechanisms and a subset of purposes, and then we can find distances only with respect to these. So this can slightly enable a proving approach. The second thing we've been thinking about in terms of the surprisal, this is related to the surprisal you mentioned, because it's surprising to see these two mechanisms together. It's surprising to see this mechanism in the context of this purpose. Kind of surprising in a language model kind of sense, but learned on top of a corpus of patterns. Another thing we've been doing is looking at citation-based approaches. So there's work on pattern novelty based on citation, like trying to quantify what recombination means. There's quite a highly cited paper there, where you, for example, look for patterns citing across very different parts of space. Or patterns that have been cited after they came out, from different areas. So this means it's broad interest coming from many different directions. But that's stuff we've been looking at. And one interesting part that's directly related to what you're getting at, I think, is quantifying the delta. So what in this patent is the new element with respect to prior art? And I think that ties to what I spoke about that I'd be interested in doing, which is decomposing ideas. So if we had a good ability to, like, any idea can, or most ideas can be described kind of a tree or kind of a flow chart. We did this, we added this, we went to that. If we can extract these for any ideas, then maybe we can decompose ideas and then identify what's the delta, what's the novel element being added. That's like this algebra. So take this idea minus that idea, you get that. How novel is it?
Some examples as well. So for example, the USB powered by pulleys, quote unquote, give me a break. We know from the Media Lab from maybe 1989, people with sneakers and motion, and that's a really old idea. And simply attaching it to a USB charger is not really novel or interesting to me. If someone said, hey, check it out, I have a new material you can make shirts out of. It has piezo effect, so in the wind, when it blows, it generates 14 kilowatts. Now, that's like holy cow, why didn't I think of that? That's cool. And so you want to get to these examples, like that would be really mind-blowing. It's the same, like it's ambient energy, but the shirt as a sail, and crinkling in the wind, generating 5 kilowatts.
Did you come up with that one? Did you come up with that one just now, or?
Yeah.
Wow,
okay.
Let's patent this. Let's patent this.
So I'm saying I can sort of quickly spot something that could jump out as like, oh please, I'm trying to patent that, versus that's really interesting, and if you have a way to do that, you should. For patent law, you want to share that and license it. Share it with the academic community, scientific community, and you can license it because you deserve the license. Versus you're taking this yawning old idea and sort of slightly modifying it.
Yeah.
So the idea of a jump and what would be interesting, getting into the aspect of what we call interestingness or surprise.
Yeah.
I found missing from a bunch of your work, and I'd love to see that direction.
Yeah. So in a sense.
You're talking on the slide there. Throw it here. Okay.
No. I mean, in the sense that this is what we're trying to do. We're trying to quantify it in a sense, but there's much more to do. This is indeed work in progress, and one of the features we're trying to get in there is how did this patent change the language distribution of what followed, for example, and quantify this. How surprising is it in multiple ways, and how did it change what came after that, and how different is it from what came before? But I agree that there's much more to be done there in terms of actually breaking it down to what is really the new aspect. So we may get to that, or maybe later, later stages.
I kind of have a different flip on this. It gets to the same idea, but I've been asking some people here what do they think is really good research. One answer I got was, it's when you found a contradiction. This field believes this, and that field believes that, and they're believing opposite things, often in different terminology, which makes it hard to uncover. But so these surprises are when you point out that contradiction and you take a side. Mm-hmm. And I'm wondering with this if you could actually do that, because if you build these knowledge graphs, rather than trying to come up with some new connection, if you can take this knowledge graph and find contradictions in it, which would require unifying orthogonal terminology for the same thing.
Yeah. So actually, in all the theory and literature about recombination, they come from a biological often or aspect that also physicists and biologists write these kind of papers, at least the canonical ones, and they talk about like modeling recombination, which comes as an analogy from biological processes, and you can think about how hard it is to combine two things. So the easy things that are the things that are easy to recombine are going to be the less surprising, innovative ones. The things that are hard to recombine, which you can see is a kind of contradiction, because it's not quite a contradiction. If it was a true contradiction, so you wouldn't be able to do that because you get something that's false. But it's a contradiction in the sense that it doesn't appear intuitively that you would be able to combine these two things or naturally fuse them together. Is that related to what you're asking?
That's interesting. So you're saying something appeared to be a contradiction just from...
Because of our understanding right now, but that's the true novelty in changing our view. Yeah.
Yeah, that would be, if you could do that.
Yeah. Yep.
Just curious if you have thoughts on how these inspiration techniques and the ontology could be applied outside of these sort of hard value things like science and more creativity or education.
Yeah, I had actually a backup slide which probably doesn't appear here anymore, but so I'll just tell you my thoughts there. Think about analogies between historical events. Think about analogies between pieces of literature. Take analogies between Wikipedia pages, one describing a battle that happened 5,000 years ago and one that happened 50 years ago. Think about analogies between battles in a football match. Okay, so you have these two fervent teams chanting, and there's even physical action going on there. So the abstract structural relations can go across not only technology in a more general sense. Analogies between people, so you can cancel out some elements of people and find analogies with respect to certain properties. So one of the things I'm interested in is also analogies between events and stories. For example, a good data source would be Wikipedia or news events. Does history repeat itself? That's like my catchphrase for that one. Yeah.
You can you imagine if you did have these delta scores and so on, you can actually
How-
have the patent office use them themselves, like give me a break notion.
Right, yeah.
And,
Or quantify the novelty in some political agenda, how novel it is with respect to, what everyone else has been saying. So,
yes.
To do that, one of the interesting ways, we're just whispering here with Kwan-san, is we've extracted many tens of millions of non-patent literature citations from the global patent corpus. And with Kwan-san's ontologies, we could actually get distance matrices between the different scholarly citations within a single patent and look for patents that have the most distant types of
sure.
scholarly references.
Yep.
And that might be really a fun empirical study to do, just to see.
yeah,
if it gets you
this is something we're directly looking at. We have these features. They can be, there are two main metrics. One is called originality. So, and the other one is more related to recombination. And so basically measuring how diverse the incoming citations are and how diverse the outgoing citations are. These are two well-known metrics in economic literature. It's interesting to bring them into AI and take our own kind of approaches that we know of and make this a bit better. Yeah.
Okay. I think we've reached quiescence. Thanks very much.
Thank you.